we're given parametric equations, so x and y in terms of this third variable or parameter, theta, where theta is between 0 and 2 pi. So immediately we see we're working in radians, and we're asked to find dy by dx. So for this, we can use the chain rule. Dy by dx is going to be dy by d theta by dx. And d theta by dx is actually 1 over dx by d theta, so I could just rewrite it like this. Now, if y is 3 sine theta, and I don't know why I'm doing this one first, but that's the one I chose because it's at the top, I guess. So dy by d theta is going to be 3 cos theta. When I differentiate sine, I get cos. And meanwhile, dx by d theta, cos goes to minus sine, so I'm going to get minus 2 sine theta. So my gradient dy by dx is going to be 3 cos theta over minus 2 sine theta. And I could write that as minus 3 over 2 cot theta if I wanted, but I think this is fine. Next, we're told that the tangents to the curve at the points P and Q pass through the point 2, 6. Now I actually know that if you just get sine theta and cos theta, you get or if the number's the same, I think you get a circle. I believe this is going to be an ellipse. It doesn't really matter, but I'm just going to draw a little picture of what's going on. So we've got a 1 point here and another point here, and then we've got some tangents, and they're going to meet here at 2, 6. Okay, so we can focus. So maybe let's say this is P and this is Q. So for P and Q, like both of them, we're going to get y minus y1 is equal to m x minus x1, because that's the point gradient form of a tangent. So for us, it's going to be y, but actually y is 3 sine theta minus y1, which for us is 6, is going to equal 3 cos theta. That's our gradient, minus 2 sine theta times x, which is 2 cos theta, minus 2. And this is going to be for some theta. Okay, that's not quite the tangent itself. You'd have to put theta in, and then you would get these straight lines. But like for some value of theta, that's going to be the tangent for P and for Q. And yeah, basically the theta is going to satisfy both of these equations. So now we need to rearrange it to try and get 2 sine theta plus cos theta is 1. I'm first up going to multiply through by minus 2 sine theta. So that's going to give me minus 6 sine squared theta plus 12 sine theta. And that's going to equal 3 cos theta times this bracket, which I'm now going to expand. I'm going to get 6 cos squared theta. Then it's going to be minus 6 cos theta. Okay. I can actually divide through by 6. So minus sine squared theta plus 2 sine theta is going to equal cos squared theta minus cos theta. And we see two of the terms here now. We've got the 2 sine theta, we've got the cos theta, it's just a negative. So I'm just going to rearrange it to 2 sine theta plus cos theta will equal sine squared theta plus cos squared theta. And that is actually identical to 1. So that is what we need to do, get this equation here. Nice. I think that's quite tricky actually, because you're normally used to finding just tangents for a specific coordinate. But here, because we don't actually know what the gradient is, we've just got it in terms of theta. Like I'm not this equation here is like a bit less obvious than normal. But we're just using, ultimately we still use y minus y1 equals mx minus x1. So I suppose you could argue that's like pretty much the only thing we could have done. Substituted in. We got our tangents. It's just there in terms of theta, which we don't know what they are, but we know both tangents satisfy that. And yeah, so the value of theta will satisfy this equation. And then we rearranged it to get 2 sine theta plus cos theta is 1. In part C, we're then asked to find the values of theta at the points P and Q, which is another way of saying solve this trig equation. Now, the thing is, here we have a sine theta and a cos theta, but it's not equal to 0. There's a very special way of dealing with it when it's equal to 0, and you can turn it into an equation in terms of tan. But when you have a number here like that, there's a different technique, and it is your r sine theta plus alpha, or plus or minus, or it could be cos. It's one of those four things, and that is we need to use the addition formula. Basically, we can absorb the sine and the cos into a single term of sine or cos, and then we can solve it once we've got that. So here are my addition formulae, and I can see that I've got sine, something times sine plus 1 times cos. So it's looking like I want to use the sine a plus b one. I don't have to actually. I could use cos a minus b. That would be quite natural because I got a plus there as well. But I'm going to use the sine a plus b. So let's just write down. Um, we've got sine. I'm just going to write it down. Sine a plus b is equal to sine a. I think this is a good starting point. Cos b plus cos a sine b. So for me, right, we normally go with sine, therefore r, stick an r in there, r, because these are never greater than 1, but for us, we do have something greater than 1, so we need to multiply by this constant. R sine theta, we normally use then like alpha, is going to equal r sine theta cos alpha plus r cos theta sine alpha. And we can compare this with the equation up here, 2 sine theta plus 1 cos theta. Forget the equals 1 for the moment. So for us, we have sine theta here, and therefore we can say that it must be that r cos alpha is equal to 2, because that's what we're multiplying sine theta by. And then I've got cos theta here, and therefore r sine alpha is going to equal 1. Yeah, and so we're able to rewrite it in the form r sine theta plus alpha if we can work out what r and alpha are. And there's a very specific way to do this. In fact, what we do is I'm going to rewrite it like this. We can first of all divide them, because if we divide them, the r's cancel. So when you get simultaneous equations where you are multiplying things, instead of like adding or subtracting the equations, you divide them. Because for us, that then gives us tan alpha is equal to a half. And we can do inverse tan. I've put by the way, you've got to make sure you put your calculator in radians mode. Very easy to forget that, but it did say right at the start that theta was between 0 and 2 pi, so that's implied. Okay, so I get 0.4636. And then for r, you could put it back in, but like a better way is to actually square and add them. So we've got r squared sine squared alpha plus r squared cos squared alpha, which we can then factorize out, is equal to 1 squared plus 2 squared. This disappears, that's why we squared and added them. So we've got r squared is equal to root is equal to, sorry, I'm taking the root when I shouldn't have. We've got r squared is equal to 5, and so r is equal to root 5. We don't take a plus or minus or anything. There's no need for that. And that's it then. So we've just shown, so 2 sine theta plus cos theta is actually identical to root 5 times sine theta plus 0.4636. And therefore we want to solve not this thing here, but root 5 sine theta plus 0.4636 equal to 1, because that's what I had right at the top. And remember, right at the start, it told us that theta is between 0 and 2 pi. I forget whether it's allowed to equal both. No, it can't. It's it's less than 2 pi. Probably won't matter, but let's, strictly speaking, we should do that. Right, so now we can solve this. So sine theta plus 0.4636 is equal to 1 over root 5. So it's going to be inverse sine of 1 over root 5. Which is 0.46364. Which actually, that caught me off guard a little bit, but in fact, theta equals 0 is going to be a solution. And you can see when you put 0 in, sine 0 is 0 and cos 0 is 1. So that will actually work. Now, don't forget, there is another answer. I don't use CAST diagrams typically. I just draw the sine graph and have a little look. So we've got a solution here. And there's going to be another one at pi minus 0.4636. So pi minus the answer. But then that will give me theta plus 0.4636. I'm going to have to minus another one, so I can basically just minus 2 lots of it. And that gets me 2.21. So those are our values of theta at P and Q. It's a nice question, this, because it starts out with parametric equations and it brings trig back in. I like it. But yeah, lots of things to think about, but I hope that makes sense.